Hello and welcome to another WJEC A level physics question. This time it's question 7 from May 2018's Unit 1, and it's a question about energy transfers, work and power. And it's about a roller coaster ride at the theme park. We're told in part A of the question that a motor of power 65 kilowatts pulls those carriages of mass 2,600 kilograms from A to B in a time of 32 seconds. And first of all, we're asked to show that the work done by the motor in 32 seconds is approximately 2 megajoules. Well, power is energy transferred or work done per second, so the work done is the power times the time. So we got 65 kilowatts, 65 times 10 to the 3, must turn it into watts, times 32 seconds. And if we put that into a calculator, we get 2.08 megajoules. Next, we've got to calculate the efficiency of the mechanism, assuming the carriages are momentarily at rest at B. Well, to calculate efficiency, we divide the output energy by the input energy and multiply by 100 to get a percentage answer. The previous answer at 2.08 megajoules was the input energy, so let's first of all calculate the output energy. And the output energy will be the gain in gravitational potential energy of the carriages as they've been pulled up that slope. There's no gain of kinetic energy because the carriages are at rest at B. So let's put in some figures. 2,600 kilograms, 9.81 for G, and delta H from the diagram 42 meters. So putting those into a calculator gives us an answer of 1.07 megajoules. So we can calculate the efficiency by 1.07 over 2.08. They're both megajoules, so there's no need to put the megas in, and multiply it by 100. And again, if we put that into the calculator without any rounding, we get ourselves an answer of 51.5%. Obviously you get error carried forwards from previous parts of the question. For part B of the question, we're told that at B the carriages are disconnected from the motor and they move under the influence of gravity for the rest of the ride. In moving from B to C, a distance along the track of 36 meters, they experience a mean resistive force of 2.8 kilonewtons, and we've got to calculate the speed of the carriages at C. So if we go back to the diagram, what we've got is basically going from B to C, the carriages are losing 42 take away 12, 30 meters worth of gravitational potential energy. So let's calculate that first of all. So the change of gravitational potential energy, mg delta h again. So 2600 times 9.81 times that 30 meters. And that gives us 0.765 megajoules. Now if there was no resistive forces, all of that energy would turn into kinetic energy, but there are resistive forces, so a certain amount of that energy is going to be converted to usually thermal energy due to the work done against those resistive forces. So let's calculate the work done by using W equals Fx, technically Fx cos theta, but the cos theta is 180 degrees, meaning that we get a minus answer here, which again just points out that we're actually losing energy because of this work done. So we got 2.8 kilonewtons multiplied by a distance of 36 meters, and that gives us 0.101 megajoules. So the difference between those two is going to be the final kinetic energy, and let's show some workings there. 0.765 minus 0.101 comes out as 0.664 megajoules, or if you just prefer 664,000 joules. So finally now we can calculate the kinetic energy. Kinetic energy is half mv squared. So quick rearrangement, V is going to be the square root of 2 times that kinetic energy divided by the mass, which was 2600 kilograms, giving us a final answer of 22.6 meters per second. Thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments below. Goodbye.